I'm Elliot Rouse. I'm the professor for this class. Welcome to Robotics 311, how to build robots and make them move. You guys probably know this is the first time this class is being taught, which means it was invented over the last 3 months. So this is going to be fun. It's going to be a bit of an experiment, but I think we'll kind of work together and see how it goes. This is, as you'll get a feel for in this lecture, this is a complex project that you're about to embark on. So we have a lot of help to provide, and we'll kind of take it one step at a time. Okay, so let's get started. Today we're kind of review the syllabus and kind of some policies. We'll begin with basically a high-level introduction of sort of the first few weeks. What we're going to do for the first few weeks, we're going to motivate that. So there's a few people that are out from COVID and other reasons, but this is a super important lecture. So if you talk with anybody that wasn't here, you have to watch this lecture. It's going to be really important. We're going to do a quiz at the end. And we're going to do a quiz basically every lecture, I think, but it's not going to be graded. We'll go over the syllabus in a second, but it's not going to be graded for correctness. It's just going to be graded for, it's a tool for me to assess kind of how you guys are doing, how you're tracking kind of what's going on in the lecture. And then it also helps me keep track of attendance. So I'll do that at the end, and I'll assign homework 1 today, which mostly will consist of doing the Basics 1 and Basics 2 training. Okay. What I was sort of saying before is this is kind of how I do lecture notes. This will be an experiment. So how many people here are sophomores? How many are juniors? Awesome. How many are seniors? Even better. Okay, that makes me feel better. So I've only taught juniors and seniors and grad students. So I've never taught sophomores, which means like I'm a little bit less clear on kind of what you guys know. So help me understand that. Help me, if we go too fast or anything, just stop me and help me understand kind of where we are. This is an experiment. Like I was saying, this project is like a little more intense than what I think we would typically do in an undergraduate robotics class. That being said, we will give lots of help. So we're not gonna just turn you loose. We'll give you help every step along the way. And I think taking on a project like this will show you like many, many interesting things that you wouldn't see in a simpler project. And this might be more along the lines of the types of projects you might be interested in personally, or types of projects you might be doing for a company in the future. Things that are kind of less like a typical, student-based simple problem. So yeah, as an experiment, policies, I think it makes sense for you guys to raise your hand. This is a lower class number also than I usually teach with. So let's try raising our hands, but if it turns out that like a conversation, you just want to say something as we're talking, we can maybe see how that goes. With this many people, I don't imagine it getting too chaotic. How many people have a laptop? Does anybody not have a laptop? Not have access to a laptop? Okay, I feel like now in 2022, we can depend on people to have laptops. So I'm glad you guys do. If anybody doesn't have a laptop or loses their laptop or for some reason needs one, I have a spare, and then also the IT department has spares. But this class will require a laptop. You'll do a lot of stuff with your computer. How many people have Macs? And everybody else's PC? So a handful of Macs. Okay, that's all right. I know PC better, but some of the other people that help me with this course will know Mac better, so I think we'll be fine. The programs work on both. You can use your laptops in class, that's fine, just keep it on course content for everybody's benefit. One thing is that I cold call people, or I have a lecture format that's more of a discussion. And I think I do that because I think it's great for learning on your side, and I think it keeps things a little interesting. So I'm going to ask you to engage and talk. And if people don't want to do that, then I will cold call. But usually I don't have to. Usually I say this, and then I never have to cold call. But that's, as you'll see in this lecture, this will be sort of a conversation. And then the way that I do slides and lectures is sort of like this. This is not one that creates these PowerPoints, and then I blank them out to have stuff for me to write down. That keeps the pace of the class a little slower. So that's how I do this. We call these worksheets, the ones with the blanks. those are uploaded to Canvas before class. So if you want to use them, you can. You can print them out, fill them in, or you can kind of use them on your tablet or computer if you can do that. Unfortunately, I can probably only get those posted like an hour before class. I'll try to get them done as soon as I can. Usually, I think like the earliest it would probably be is the night before. But so if you want to kind of follow along this way, let me know, or like tell me how this is working, the lecture thing. If it needs adjustment, we can update it. But if you go to Canvas, lectures, or lecture worksheets, this lecture is there with all the blanks that you're going to see. And then after class, I will post my version of a lecture, the one that I look at with the blanks. So if you're the kind of person that likes to take notes and that helps you learn, do that. If you're the kind of person that kind of like just wants to listen and engage that way, that's totally cool. You don't have to take notes. My versions of the notes will be uploaded. Cool. So if the 1 hour before, if that's causing trouble, just let me know. That's a little bit flexible. Okay, now we're gonna go to the syllabus. It's long. I don't know if you guys have seen it posted. But okay. All right. You have the online, there's kind of the text box version of this, but you guys know who I am. I'm the professor of this class, Elliot Rouse. We have a GSI. His name is Eve. He's in the back. He's going to help save you from all of your technical difficulties. We also have another person who worked with us. His name is Senthir Raj. I think he's going to come at some point in this lecture. He also worked heavily with us on the development of this course. And the course development will be ongoing. So you'll see them. You'll see Eve and Senthir. Senthir will probably come in a bit. This has lectures and labs. So this is obviously a lecture, Tuesdays and Thursdays. Labs will be on Wednesdays, 12:30 to 2:30, I think, in the robotics building. This part of the class will focus on like didactic. Theory is probably too strong, but it's going to be teaching, didactic style of teaching. You're going to learn like course-based content like a normal class. The labs are hands-on. That's when you're actually going to work on your ballbot. And it's possible we have to commandeer some of these lectures to work on the ballbot. It's sort of unclear, but the intent is that the labs are where you work on your ballbot / like go through specific labs that we build to illustrate certain concepts. And then we'll kind of see how the ballbots come together. In the syllabus and notes kind of when I'm sort of expecting the ballbot to be assembled, fully designed and assembled. But we'll get to that. Attendance, mandatory. You don't necessarily have to come to class. I would definitely prefer it. And really, unless there's like a sort of extreme extenuating circumstance, I think that's the kind of the rule because we're going to do these quizzes. But if you're not feeling well or you're uncomfortable coming to class, like let me know, we can work it out. This class right now, there's 2 people who got COVID, so this class is being live streamed for those that wanted to join remotely. We can kind of continue to do that, we'll play it by ear. I think you will learn a lot more if you are here. And this class is going to be like a lot of learning. So I think it's best if you guys come. Attendance is mandatory. There's no textbook for this class. And this is a little bit of the challenge of creating a robotics department / robotics curriculum in the very beginning from scratch. Is that it's sort of unclear what, in mechanical engineering, electrical engineering, everybody knows the curriculum. It's been around for 80 years and basically unchanged. So this is totally different. No textbooks haven't yet been written. Like they'll sort of become more available over time. This class could turn into a textbook potentially in the future. But as of now, there's no textbook, and instead, I have a bunch of resources for you. And how you'll study or how you'll learn will be both lecture content and sort of our discussions, and then also these resources. One of these resources, this guy, is a bachelor's thesis from a university called ETH Zurich, Switzerland. It's a really prestigious technical university. That bachelor's thesis is 2 students, I think, who built a really impressive version of this, I think in undergrad, but I'm not quite sure since it's Switzerland. But that is posted, and all of our math and descriptions will follow their math and descriptions. So our systems are very different, as you will see if you read these theses, but the underlying dynamics and mechanics, and somewhat even the control, will track. So that's a long document that's just on the building of this ballbot. So it's worth reading if you have the time. This is about learning how to code. Who's comfortable with coding in Math? Who's comfortable coding in Python? Awesome, fantastic. Who's comfortable with the Linux command line? Awesome. All right, this is good news. That's great. So this is about, if you don't know Python or Raspberry Pis, like these are worth taking. The Code Academy is an awesome tool to learn software engineering and different sort of software concepts. Everybody knows what Raspberry Pi is? Who doesn't know? It's a small single board computer the size of a credit card. So it's as powerful as a laptop from probably like a decade or two ago, but it's a small single board computer. It runs a Linux operating system. That's what you will use to control your ballbot. So eventually you'll get all these things, but that's what a Raspberry Pi is. It's gonna come up a lot. We have a lab kind of dedicated, not this lab, but next week's lab is dedicated just to kind of building your own Raspberry Pi system, and we'll kind of talk about that. This is a book on feedback control, Ostrom and Murray. It's a free PDF, and it's really well done. It uses, who's taking feedback control? Awesome. It uses a different notation. It uses state-space notation, which is a different type of control notation, which you may not see in undergrad. It's usually like in electrical engineering you might see it, or robotics you might see it, but mechanical engineering typically you would see that in grad school. I'm also part mechanical engineering. But it's a great book. So it's uploaded to Canvas/resources. And then this, Mesner and Tilbury, this is an awesome website that has lots of different MATLAB tutorials on control. That'll come up later, but it's cool if you haven't seen it. It's really well done. It was developed in part or led by Don Tilbury, who's now the department chair in robotics. So that's a great resource. Okay, quizzes. Like I mentioned, we'll do quizzes kind of hopefully every lecture. Short, high level. Try to remember that what I'm trying to do is assess whether this is working, whether you guys are tracking me and my pace is okay. So just kind of give an honest answer, and that's all we want. You won't be graded for correctness. There's no final in this class. The project will be the final. There will be a midterm, which is sort of like 2/3 of the way through the class. So that's going to focus on some of the sort of more theoretical concepts. It's on November 8th in class. You guys will form teams of 2. If you've noticed in the syllabus online, there's already a link to a spreadsheet where you can start filling in your groups. I think like I'll let you guys choose your own groups. If anybody thinks they'd rather me randomly assign them or facilitate their assigning, just let me know, we can do that. But since you're gonna spend a lot of time in these groups, and you guys are kind enough to experiment with this class, I thought it maybe made sense to let you guys choose your own groups. But we'll stick with groups of 2. So that means that like, with a group of 2, you're gonna do a ton of the work. If the groups get larger, typically I see teams divide and conquer, which means each student gets a experience kind of in a rather narrow part of the project. So that's what we don't want in this class. We want everybody learning everything. So you also create a final report, which is not meant to be a huge writing assignment, but it is meant to like capture your design decisions. So you'll have some, brief introduction, sort of a 1-page introduction, and then there'll be kind of a page on different aspects of the course, which you'll learn as we go through the course. But as you're building your ballbot and making your decisions, you want to be tracking those decisions you're making so that you can refer back to them. And if you have to justify a decision, you know why you made it. So just make sure you keep notes. We'll talk through this. This will be clear to you as we go, but there will be a report at the end. Honor code. So you can share within your own team, you can share anything about the project. Copy paste within your own team, no, it's okay, it's fine, as long as it's about the project. For homeworks and other things, obviously that has to be done separately, no sharing of code especially. That's kind of like a normal homework assignment. You guys can work together, but no sharing of anything. I think you guys know the rules. This class will use the makerspace in the robotics building. So that'll come up more and more, but there's a in robotics building, 114B or 1141 FRB. FRB is Ford Robotics Building. That's the name of it. And we'll use that for all the manufacturing. This class will focus on kind of rapid prototyping, which is a section of manufacturing that are like quick and easy tools, as opposed to standard sort of mills and lathes that you might use. We're not going to do that stuff. Makerspace is led by Alyssa. I think you'll get to know her. We'll talk more about training in a minute. This is the link. As you'll see in homework 1, which I'll post today, a huge part of your homework assignment is to complete Basics 1 and Basics 2 for the Wilson Center. Who's completed those? Awesome. Okay, so you guys are off the hook. But everybody else has to complete that so you can get access to the makerspace. I think there might be an additional orientation associated with the makerspace itself, but I'm going to meet with Alyssa and schedule that. So stay tuned for that. We'll use the makerspace a lot. All of you will gain, get an understanding of if you want to make something, how does that work? How do you design it? How do you manufacture it? What tools do you need? What machines? That kind of thing. We will provide you with basically everything you need for this project. So soon, you'll get a tote, and that tote will have all the parts inside of it. And then you'll sort of slowly go through those parts, and we'll kind of begin to build this ballbot. What I need you to do is not to lose things, especially the like important stuff like motors, like electronics, IMUs, like that kind of thing. So keep that stuff because we need it. Wheels, we need them for the next version of this class. So if we lose all those things, I'm gonna get in trouble and not be able to teach this class. There's 2 sections of Canvas I noticed. We're only gonna use the 001. The other one I hid, so maybe you guys won't even see it, but I've never taught a class with a lab section before. So they create a Canvas page for the lab section, I guess. That's maybe normal, but we're not gonna use that. Everything will run out of this class's Canvas. Okay, like I was saying, you gotta sign up with your teams. The link is here. I'm hoping you guys can have your teams done by today or tomorrow. So we kind of want them to happen relatively fast, so we're gonna jump right in. So if there's any trouble with getting team members, like I said, let me know. This is about diversity, equity, inclusion. If there's anything that I say or do that's sort of like uncomfortable or offensive, just let me know. That's okay. That's a normal thing. And then grade breakdown. This should be shifted down a little bit for some reason. But that's how we're gonna break the grade down. Homework is gonna be 20%. There'll be approximately 6 homework assignments, first one assigned today. Class participation will be 10% of your grade. So that means like in this sort of didactic version of how we talk through class, you have to participate, or at least I want you to participate. I want to incentivize you to participate by making it 10% of your grade. The project and report, 40%. So that should tell you like that's kind of the focus of this class. And then there is no final exam, and midterms at 30, which is, I think, that's usually what my midterms are, about 30%. Any questions on sort of the logistical stuff, class stuff? No, okay, so below this is sort of the schedule for everything in the class. So you're welcome to have a look. It'll sort of give you an idea of what we're doing and when. The labs are in blue. The labs it's pretty clear to us what those are. The teaching, it's also clear to us, but what's not super clear to me is how long it will take us to go through this content. So if you'll notice in the syllabus, for example, there's nothing here. From November 17th to December 8th, there's really like nothing in the actual lecture content. But what I think is gonna happen is we'll go through content much more slowly than I have it written. So all of that will sort of push forwards throughout the whole class. That's my expectation. So I was hesitant to add any other content to this class because there's already a lot. Yeah.
If stuff gets delayed, is there a chance the midterm exam will have to be pushed further down, or the midterm exam be that date regardless?
No, I'd say, I mean, we'll have to kind of wait and see. It could get pushed if it seems that that's better. That's really all about like what is the best way, what's the best time to test you on this material.
Yeah.
And that's really, to me, that's the only thing that matters. Is that we don't want this material to come too soon. So if it seems like that's happening, we would delay it. And then that may happen. Any other questions? Okay. Awesome. The last class we'll do some sort of competition. Haven't quite figured out what that's going to be. It sort of depends on how like agile and successful these ballbots are. One version of the competition could be they just have to balance for as long as they can. If balancing is challenging, then that's kind of what we could do. That's neat. Or we could have like it balances as long as it can, and we like blow air across them or sort of disturb them in some way and see if we can get their control systems to reject that disturbance. Another potential option would be like a course that we have people sort of drive around if we get the actual rolling of this thing completed. We are close, so we've been building this over summer. We are close to have it rolling, but it's challenging. We have it very stable, but the rolling part is a little bit of a challenge. Once it gets rolling and there's a net torque on it, it wants to accelerate, and then it goes faster and faster and faster, and then it can't sort of stop itself and it falls over. So that'll be like a work in progress we all do together. My guess is we will have the rolling controller sorted by the time you guys are ready to do it. So that'll be fun. Last class is some sort of competition. We'll see how that shapes up. Okay, that's all for the syllabus. Now we're going to like switch back to actual lecture content. Okay, so this is sort of what the slides more look like. They look like sort of blank. This one has all the blanks, or everything blanked out. But yeah, this is sort of the difference. And when I post it, those won't be there. Okay, so this class about modeling, specifying, so choosing the components, designing, solid modeling, manufacturing, and controlling this ballbot. So all the steps to build a robot. Specifically, I kind of want to like list the questions that you'll be able to answer. And these are kind of the guiding principles that we have used to create this lecture content. So first it would be like, how do I determine the proper design for my application? When you think about design, a robot that may be being designed, are there any attributes of that robot that you think, when I say like the proper design, are there any attributes of that robot that might seem like it has to be chosen carefully? These could be like general things. Yeah.
I guess wheels based on its terrain.
Absolutely. So wheels. So let's think about what the wheels do. And maybe in this particular, wheels is definitely one of them. It factors into something I think bigger and maybe more general. So the wheels, we have like a ball, 3 motors, or 3 wheels that attach to 3 motors. But what the wheel is really doing in this application is it's really a form of a transmission ratio. So the things that I kind of would want you to say here, in addition to the specifics like wheels and other dimensions, would be the transmission ratio is key. So when you design something, a key decision is the transmission ratio that's used. Well, that'll come up for why that's so important. Does anybody have any ideas about why the transmission ratio is a really important feature? Yeah.
Because we'll have like a trade-off between torque and speed.
Yes.
We want it to be powerful, but also like responsive.
Right. So transmissions are really giving you this trade-off between torque and speed. There's somewhere where you'll have way too much torque and not enough speed, or way too much speed and not enough torque. And you have to balance these appropriately. The transmission ratio comes into play. It also governs the response dynamics. So we care a lot about transmission ratios in our work. We care a lot about what the robot feels like to the outside world. And transmission ratios are a big factor in that. Transmission ratios also like govern the physical design oftentimes. In this project, less so because it's just a motor with a gearhead on it. But in other systems you may work on, the physical design may really be driven by its transmission ratio, what it looks like, what the wheel diameter is, for example. Okay. Also, for example, what motor should you use? that's another big question that you often have to answer. And this might not be motors, maybe it's a pneumatic system or an air-powered system. All of these same rationales would apply if it was a different source of effort, not an electric motor. And this class will focus on electric motors, but the rationales are all the same. Okay, how can I design something and have it made? Or make it yourself? How can I predict the performance? Slash characteristics. If my handwriting is poor, so I know that. So just if you can't read it, just tell me and I'll erase it and rewrite it. Also, like this thing makes it worse, not just me. So for predicting the performance, I mean, if you're building a system, you want to know before you actually design it, manufacture it, and control it, that at least you have high confidence it's going to work, that it's the right system. And oftentimes, I think in undergrad especially, we don't spend enough time on this, about why something might look the way that it does or have the properties that it has. So this class will kind of teach you how to do that. How do we predict the performance, which helps us know if we're meeting our objectives. How do sensors, microcomputers, etc., work together to control a robot? What sensors and signal processing are commonly used? What's an example of signal processing?
Maybe a Kalman filter.
Yeah, I'd say more generally any filter. Like a low-pass filter, all those would be like generic signal processing. In this class, we won't do so much with common filters, but we will use potentially definitely low-pass and maybe high-pass filters. So we'll talk about that. How can I write strategies or write control strategies? That live on a microcomputer? And how can I control multiple axes with different instructions? What's multiple axes mean? Anybody know? Maybe in the context of this ballbot. What do I mean by multiple axes? Yeah.
You just mean like the axes of movement?
That is one like interpretation, and that works. Yes, it has, we'll talk about this more in a minute, but it has 6 degrees of freedom. It can move in Cartesian space and it can rotate. So that's a common kind of way to discuss it. It also has 3 motors. And if we think about its motion, what we'll end up doing is talking about its motion in terms of 2 planes. We'll talk about this extensively. And then those 2 planes actually command these motors. So each plane ends up working separately and summing. We'll kind of talk about how that works. Like, why does that work? How can we take a 3-dimensional problem and break it up into 2 2-dimensional problems? And that seems to work well. So we'll come back to this, but this will be a big part of the class. That's one reason why I chose the ballbot, is because it has this concept, has these multiple axes. And then the entire goal of this class is this. These are the tools you learn in this class you can use outside of this class, like for life. If you think of a robot that you want to build, this will be like rather kind of more simple robots. But if you think of a robot you want to build, you have the skills to do it, the whole process. All right, what is a ballbot? Okay, a ballbot is like BB-8, balances itself, rolls. Ours balances on the top of a basketball. And it has to move the basketball, roll the basketball to move in the environment, and it has to decelerate and accelerate accordingly. It is a challenging problem. And then this is, it's a challenging problem, that represents many potential challenges you could see in robotics. So this is sort of an example for us to study, to build these tools. Why might it be hard? I'm saying the ballbot is a challenging problem. What's hard about it? Yeah.
Keeping the head balanced kind of on top so it doesn't roll too far forward and then pop off.
Yeah, it's unstable. It wants to fall over. So this system is challenging because it's unstable naturally. It wants to fall over. Yeah.
And also, like, the real world is sort of messy. Even when we have the equations down, the gearboxes could have backlash and whatnot, and it
For
just
sure. Yes. So what you're saying is true. So basically, like, real life is not the same as our ideal situations we often study in class. That is true. That is true for like all robotic problems. So not just this one. These things I'm talking about are specific to the ballbot, but that is a true statement, and you guys will see the differences between modeled versions and actual versions and the real life version, and you'll get a feel for that. The other thing is a harder one, but it's the concept that this robot is under-actuated. It has 6 degrees of freedom. Everybody tracks what that means? Who doesn't understand the concept of it has 6 degrees of freedom or degrees of freedom in general? Okay, what are its 6 degrees of freedom?
It's like X, Y, Z moving around, and then all the different, I don't know how you would call them, but like angling.
Yeah, the different rotations about the yes. So it's 6 degrees of freedom. How many motors does it have? 3. So can we completely specify its position and orientation? No, we can't. We can only use 3 motors, which means it has many solutions for a given desired output. So that makes it more difficult. It's much easier to solve things that have as many degrees of freedom as there are actuators. I'm going to say it's under actuated. I'll say more DOS than actuators. Okay, the goal is to get the goal of your teams is design and manufacture. You want to get it to balance on its own. And ideally, we'll get it to drive and steer using a remote PS4 controller. So that's the game. Design and manufacture, balance control, so balancing on its own. We'll call that low-level control, balancing on its own, and a higher-level control, navigating or moving in the environment. So yeah, this is what I keep drilling home, but this is an example. So this ballbot project is just an example of many potential robotics problems. Okay. Robots are a collection of subsystems that enable some sort of application. We'll leave the definition very general. And then within these collections of subsystems, here's an example of a ballbot that we built over summer. What are some examples of subsystems that you see on here? Like sort of large classes of components. What's going on here? What are the things you see? Yeah.
There has to be a sensing subsystem.
Yes.
Where it notices if the ball is starting to tip over.
I'm going to call that a mechatronic subsystem,
Sure.
which is sensors, batteries, microcomputers. Yes, that is one subsystem. What's another? Yeah.
Oh, like the powertrain, the motors and
Yep. I'll call that motion. Yes, exactly. So another subsystem would be these motion components, which are gonna be like motors, transmissions, the drives. Drives are little circuit boards that control motors. Come back to that. What's another one?
The electrical part with all the wiring.
I'm gonna keep that as part of this. Anything, so now we've basically covered the electrical stuff. So anything that's sort of like sensors, wiring, computers, batteries, say it's mechatronic, there's motion,
Maybe like the chassis, the thing that holds it all together.
yes, the chassis, we'll call structures. So structures, it's the chassis, and mechanisms that enable the application. In this project, the structural components are very straightforward. They're going to be laser cut acrylic sheets with standoffs between them. So the structure for this, and then we have a kind of a 3D printed mount for the motor. The structure for this are super important, but not very complex and not very dependent on the other choices in this particular case. So for example, if you wanted to choose a different motor, there are different motors that have these sizes. If you want to choose a different transmission ratio, there's lots of different transmission ratios that can just be swapped out for this design. So in this particular case, the transmission is not, the mechanics of the system did not affect its physical structural design. And that's good, that's convenient. That's definitely not always the case. And the last one I'll say is control, which you can't really see in this picture. And for now, I'm just going to say control we're going to do later. So this part of the class, we're talking about motion, structures, and then eventually mechatronics. I'll say control will come later. So what we're kind of going to learn is a framework to go through these different subsystems, components, and make choices about them based on what they do. And these analyses are really important to do up front. So these analyses are completed before physical design. They happen before control. But they matter a ton to control. So we're about to go through this framework of how to investigate these different components of a robot, its transmission ratio, the motor that's being used. We'll kind of go through that step by step. And all of this happens before physical design and control, but the choices that are made affect control hugely. In fact, when we were doing this, the first ballbot we made was bigger, stood up higher, and the IMU sort of wasn't in the center of the axes. And we were just kind of getting started, but then we realized very quickly as we were going on, like the structural design actually matters in the layout, and we kind of redesigned it. Its stiffness matters, we also learned that. The stiffness of these mounts matter a lot. But so these analyses are completed up front, so you can make these decisions before you start design, but they matter a lot to design and control. And then Lee will teach you how to do this and be confident in your design. So at the end of this process, you should feel good about the design you have chosen and be able to justify the decisions that you made. So we're going to go through kind of that style of justification. Okay. So we're going to go through this process or this analysis framework to specify things like transmission ratios and specific electric motors and their properties. But before we can do that, we have to have an understanding of what is this robot actually doing. So we need to understand the requirements. Meaning, or in this class, Did anybody go to that thing last night, the student thing? Cool, great. So in this class, we're gonna focus on what I will say like is the medium to low level aspects of robots. Robotic systems oftentimes I will say like higher level intelligence, machine learning based control, navigation, localization, those kinds of things. This class will not touch those concepts. Those types of higher level control would sit above what we're gonna do in this class. And that's typically the way that it works. So anything, for example, an autonomous vehicle that's making decisions about what's happening, that's sending information to sort of a mid-level and low-level command or controller to execute those commands. So this class doesn't have any artificial intelligence in it, no machine learning. It's just, we want the robot to do a task, and we want it to do it well. Okay, so in this class, we focus on medium to low level parts of robotic systems. Is that clear to you, like what I mean by that? Okay, good. So meaning higher level perception, AI-based control would not be a part of this class, but could still be included. Meaning like if you wanted to, like you could eventually add these higher level perception based style control strategies that they would need a functioning sort of mid low level controller that you're building. So this class won't touch on it, but if you wanted to add it, you'd still be able to. Okay, so in the medium to low level, what does a robot have to do? It has to do a task. So it has to do a task. And I mean this sort of on a more fundamental level. It has to do a task on kind of a fundamental level, which may mean it has to achieve some motion profile or some force profile or maybe some set of output mechanical properties like a virtual spring damper, but it has a task. That task is encoded in a set of instructions. So it might look like motion, it might look like effort or flow. Can anybody think of an example of a robot that might have a similar description like that? Or anything like really like any example that might be something like that. Yeah.
Just like any actively balancing robot, just like segways or like.
Segway would definitely do it. Basically any robot, eventually the instructions have to go to a low level style instructions. Go from here to here, so a motion profile, or apply this much force or torque. So I'll just say examples would be track, a position profile, torque, force, or virtual spring damper. So it has some set of instructions, or it might be a velocity set of instructions, or position set of instructions, or force set of instructions. You guys have probably interacted with robots that mostly have velocity or position control. It's not super common to experience robots with something like force control. That's kind of a more unusual task. You might know why that might be the case. Why you don't see robots with force control much. Yeah.
We don't tend to think in forces like as people.
Yeah, that's probably part of it. Another thing is like robots also, their motion can be dangerous. And so a robot under force control has basically no constraints on its motion. It has a constraint on its effort, on its force. So it's trying to track a force and will essentially go wherever it needs to go to achieve that force. So that's it's a little more of a trickier situation with a robot, but a position profile or a velocity profile, those are a little more safe and a little more common. How about a virtual spring damper? Does that make sense? What if I had a robot, let's say like I'm a robot, my arm is a robot. One option is I tell this arm to follow a position profile. and I expect it to execute it. Another option is I have it provide a force, which then means it doesn't matter what position it's in, it's always gonna be providing that force. And then this other option I'm talking about is this virtual spring damper would be, I'm gonna tell the robot to behave like a physical system, like a virtual spring damper, for example. Just another kind of style of control. How about not examples? What are we not talking about in this class? These higher level types of control, yeah.
Path follower.
Yeah, path planning, flash following. Following could be what we're doing if it's position, but we'll say path planning and following, yeah, not examples. Autonomous vehicles, for example, are not part of this, like dexterous manipulation, not part of this, that's all other things. You know, if I'm giving a robot an instruction to take this drink and put it over there, as long as that's provided as a set of position profiles, then that's the scope of this class. If it's provided as sort of higher level interpretation, identifying that that's a drink, stuff like that, not part of this class. Okay, what is the task for the ballbot, like in terms of physically? What is its physical task? Yeah.
Stabilization.
Stabilization is part of it. I'm thinking of the other task. That's one of them. This is going to illustrate more, I think, what I'm trying to say here. So it has to stabilize, but then what if we want it to drive? It has to do something else. What does it have to do? Yeah.
Like move the basketball under it.
It has to roll the basketball. And rolling the basketball has inertia and friction. So it has to roll the mass of the ball and its own mass. So roll that mass, and it has to decelerate that mass in addition to balancing. So we'll say, how about for our ballbot? This really has to roll the ball, balance, and fight against friction. Okay. For the sake of discussion, let's pretend that we have a solution or a description of the required effort to roll the ball. Okay, it's going to come up more next lecture. So let's pretend we have a description of the torque required to roll the ball / fight friction. So normally, this is an analysis you'd have to do typically. We're going to cover it later in the class. I didn't want to go straight into it. This is the kind of dynamics of the ballbot. They're a little complicated, so we're going to give ourselves a little time to get familiar with the ballbot first. So for now, just pretend you have this. I'm going to give it to you next lecture as a Simulink model. But pretend that you have a description for the ball. If you want the ball to go from here to here with a specific velocity that you know based on that velocity, the acceleration of the ball, if you know the acceleration of the ball and its dynamics, you know the torque that you have to provide. So that we've done for you. We'll come back to it. And then we also need the max velocity. So how fast do we want it to actually roll? So that's, if we choose a speed for the ball, that will sort of filter upstream to the speed of the wheels, which will filter upstream to the mechanics of the motor. So that's kind of where we're going with this. So we need a description of the output mechanics, what the system actually has to do in terms of its motion and its effort, so torque and velocity or torque and position. And we need to have a max velocity goal. So we use this torque and velocity to understand the demands on the motor, transmission ratio, and any potential structural components, structural and mechatronic components. This is the framework that we're going to learn. is a set of analyses that kind of goes through this process. What you start with is sort of torque speed knowledge of the output. What is it going to do? Torque and speed would be kind of the fundamental descriptions of a mechanics of a system. We want it to perform this way. So we have a torque and speed set of references, which we'll show you in Simulink. So this we're going to call our application requirements. So before you can build any robot, that's what you start with. You need the application requirements. You need to know what it does, and it needs to be described in something like this physics-based description. It has to move in this way. It has to provide this much torque, something like this. So we start with torque and speed. And we're going to kind of propagate that torque and speed through the transmission. Transmissions have properties. Besides a ratio, do you know what other property they might have? That would be like the most important property. Yeah, it's efficiency. So the transmission's gonna have a ratio and an efficiency. So that's gonna trade speed for torque in some way. So whatever we had at the output, our torque set speed of the output, we're going to see that on the input to the transmission, which is here. So we're going to do this analysis basically backwards. So the motor would provide torque, and it would increase that torque usually to the output. We're going to go backwards. So we're looking at this is the torque and speed at the transmission. At the motor, also transmission. So this is still torque speed. We just mapped torque speed to torque speed. Now we have to consider the motor. So now we have, at this point, we have a description not of what the output is doing, but what the motor now needs to do. Different description. Still in torque and speed, but now we've traded torque and speed first in a certain way. That lets us look at, this is what the motor's torque and speed will be. When we learn, next lecture, we're going to learn the equations that govern brush motor operation. We can convert the torque and speed profiles from the motor side, the mechanical side, to the required current and voltage profiles on the electrical side. So this would have, we'll say, motor properties, which we're going to go into detail on. Things like torque constant, resistance, inductance, kind of thing. That would convert the motor's torque and speed to the motor's current and voltage. So this is current and voltage. That current will create heat through the resistance in the motor. So the motor's going to heat up. The next thing we have to check is if the windings will get too hot. So we'll have I'll call this thermal properties. We'll have an analysis that accounts for the thermal rise in temperature at the motor's windings. What we would then do is use this analysis framework to start adjusting the transmission ratio, investigating different motors. And then you'll be able to see how they all accomplish the task, potentially how hot the motor gets. If the motor's getting too hot, it's undersized, or the transmission ratio needs to be adjusted. So this is kind of a framework that allows us to do investigations to make these choices. The framework outcome is the motor transmission ratio let's see, power supply This framework allows you to investigate transmission ratios, motors, see the required current and voltage, make sure your design actually achieves what you want it to achieve, it doesn't burn up or catch on fire, and it follows kind of all the constraints you have on your design. For example, like an example constraint might be like you only have access to 12 volts. That would be a constraint. That will really change sort of what choices you're allowed to make. Or 24 volts or 36 volts. But so this framework gives you the infrastructure to do these analyses, to make these decisions. The end here is a temperature profile. When you look at that temperature profile, if it's getting too hot, you'll know, okay, this is not a good choice. What I'm gonna do now is we have like probably 15 minutes before I want to give you this quiz at the most. So I have like a couple more slides that I want to talk through, and we're gonna I'm gonna kind of show you this framework in some of our own research. So I'll give you an example of how we use this framework. And that's probably where we'll stop. And then we'll do this little quiz. Okay. So this is our framework. What do we need to do this framework? This is also stuff we already covered. So this is like a little bit of a review. What do we need to do this? To run this analysis or use this framework? A description of
System dynamics.
a description of the system dynamics, yes. I'm going to say the task and who doesn't know what he means by system dynamics? What do you mean by system dynamics?
Just like the way that the like actual motion of the system's going to respond to forces.
Yes. Yeah, so that is something you need, and that would be what I'm going to get. When I said I'm going to give you the Simulink model, that is this description of the dynamics. So you need some way to understand how motion, what torque creates motion. So that would be governed by kind of Newton's laws. But that's what we've done for you. But you would need that. You would need some way to understand the output mechanics. It usually comes from a physical model. We'll walk through ours in Simulink, I think, unless it just feels like it's too intense. But you need a description of a task, so motion or effort over time, and a description of the system dynamics. So we'll say you need a torque speed profile or a current, it would probably be torque speed or could be force displacement. You need some description in this world. And then also you need any electrical requirements. So like maximum battery voltage, or maybe maximum current. There are some systems that might have a limit on how much current they can allow. So what it has to do, and then any constraints. And what you get this framework. So once you build this framework, it will be used in this class, but it can also be used for solving any kind of general robotics problem. You get a framework to investigate transmission ratios, motors, power requirements. So you get a framework to investigate those things, and then you will use that framework to choose things in this class. So the framework enables the selection of a motor and transmission ratio. And you get this by quantifying the torque, speed, current, voltage, temperature of the system. And then next lecture, we'll talk about kind of modeling these subsystems. And what I want to do now is kind of talk you through a little bit of an example from our research, which I think will help illustrate how this framework is used and what importance it has in these design decisions. Any questions? Good. Okay. Why does this matter? why am I teaching you this? Or what, like we could have had anything in this class. Like in terms of content, it could be anything. So we're focusing on this thing because I think it's really important. Why do I think it's important? Do you guys, why might it be important? One's obvious and one's nuanced. It's the obvious one is we want to do what it's supposed to do. We want to perform the task. You know, it ensures proper performance. As an engineer, that does not look like proper. As an engineer, we want to achieve some technical goals. You know, this ensures that you do that. It also factors into physical design, like I mentioned. And the last one is the sort of nuanced one, which is why we focus on a lot in my research group. Enables the systems to be lightweight. You might know, like, why does this analysis enable us to like build something that's as lightweight as possible?
We don't have anything extra that we don't need.
Right. What we can do with this analysis is sort of ensure that we're running the system as hard as it can be run. That means we're not carrying any extra actuator mass that we're not really using. We're making sure we're using all the actuator mass. If any extra actuator mass isn't just the mass of the actuator, it also requires structure to support that mass. That structure affects control, affects the inertia of the system. So like mass becomes motor mass, which ascends to structure mass, becomes a really big deal if you want to building the systems to be as lightweight as possible. So this analysis is what enables us to have confidence in this. It's like saying we want to run this thing at, not at red line, but sort of at yellow line. And if we're doing that, we know we're getting everything we can out of the system. That's kind of the idea. That's why it comes up a lot. I build wearable robotic systems. That's what we're about to talk about. And those systems, their weight is key. And it turns out in a ballbot, its weight is key. Its weight is really important for the dynamics of how it moves. So it makes sense to kind of use this framework. My research group, the Neurobionics Lab, uses this framework to investigate the designs of wearable robots, like exoskeletons and robotic prostheses, all for the lower extremity. This is an example of our open source robotic leg, our second generation version of it. It was actually designed by Senther, who also led the design of the ballbot that we did. But we designed it this way to make sure it was really lightweight. These systems also, another like key part of them being lightweight is they have to carry their power supply. So anything that's carrying its power supply, then you automatically care a lot about its efficiency, for example, which also is a part of motor selection. But kind of lightweight, you want to use make a high performance system that kind of uses everything that these actuators and systems have to offer. That's what this framework provides. So in our work, let's say we want to build a robotic leg. What was the first thing we needed? There's two. Yeah.
Like metrics on the forces that typically get applied to a leg, or like that a leg needs to apply.
Yes. We need to know, like, what does it have to do? Oh, it's a human leg. Or it's supposed to be a human leg, so it has to do that. So what do human legs do? So we look to the human body. So in my world, we look to the human body to provide these torque speed relationships. That tells us what we want our systems to do conveniently. So we might need some descriptions of that. So what we're looking at here, this is the angles, so the kinematics of the ankle joint and the knee joint during walking. So this is one step, heel contact to heel contact. This part, up to about 60, would be what we call stance phase, when you're bearing weight on your leg. The rest of this, 60 to 100, would be swing phase, you're bearing weight on your other leg. Angle, velocity, torque. these are the descriptions that we would need. This tells us what the system has to do. We want a system that can do this and be as lightweight as possible. That's somewhat similar to saying we want a system that can balance and roll and maybe be as lightweight as possible, or at least reasonably lightweight. Make sense? So let's look at, okay, I've shown you the inputs to this framework, kind of in the context of our world. Let's look at the outputs. This is an example of the, oh, sorry, I switched the wrong thing. This is an example of the outputs. So now we're just looking at the ankle joint, so we're not looking at both ankle and knee, we're just looking at one. And we're gonna start on the left half of this. I'm gonna talk through these blue plots. Here we're looking at angular velocity, torque, power. Angular velocity, the output of the transmission, so this is the actual ankle joint. This is the output of the motor, input of the transmission. So this is what the motor has to do. And then this is the electrical version of it. So propagated through the dynamics of the motor to give us the electrical equivalent of what it would need, how much current and voltage would be needed to create this torque and speed. I also have shown on this different transmission ratios. Each shade of blue, so the light blue is a transmission ratio of 30, the medium is 45, and the dark blue is 60. This is the same analysis we did for this design. We chose a transmission ratio of about 45, a little higher. So this shows us, okay, it's doing 300 watts peak at the output. It's doing 400 watts on the electrical side of the input. It's doing 80 Newton meters on the output, but the motor's only doing about 2.5 newton meters, so the transmission ratio is reducing that. If we look on how much current it requires to produce that torque, we get something that looks like this. So this is kind of the output, looking at in between those blocks in that flow chart. We're looking at how the design requirements of moving like a human propagate to the motor, mechanical, to the motor, electrical. We also want to know, is the system going to overheat? What we're looking at here is the output of a thermal simulation. So we're looking at temperature over time. So now we're looking at 500 steps. So this time goes up to 1500 seconds. And we're looking at different activities. Slow walking is blue, self-selected walking, fast walking, and stair ascent. 125 or so degrees C. That's what we're saying is as hot as we want this system to get. That's kind of a rule of thumb, about 125 or 150. So what this is saying is as this system operates while someone's walking continually or going upstairs continually, the motor's temperature is going to rise. And eventually, if someone continually went upstairs, the system would overheat. So remember when I said that we want the system to be like a yellow line, not a red line? Like that's what this means, is that we don't really have the factors of safety, in a sense, to design the system such that, for example, somebody could walk upstairs forever. That mechanical demand is too high. And so if we design the system that would be able to do that, it would be much bigger and heavier. So we trade that off. So we say, okay, you can only walk upstairs for 800 seconds or something, 700 seconds, which is a long time. But this tells us kind of everything we need to build the system. If we had a constraint on battery voltage, for example, which plot would we look at?
Front right.
Top right. Voltage, this is the voltage as a function of time. So the motor's voltage is varying to produce the velocity that it needs. The motor's current is varying to produce the torque that it needs. So we would look at this system and say, okay, this system needs needs 40 volt battery. And that might be like too high for us. So we'd have to modify the transmission ratio and look lower. So this analysis allows us to start gaining insight, to start making decisions. Why does this So we have output, this is the power that the angle joint is doing. And the output, about the joint, this is the mechanical power the motor is doing. And the input to the transmission. This is the electrical power, that's the input to the motor, kind of in the electrical domain. Why does, you see a peak of 400, 400, 300. It's actually like, over 400, 450 or 500, about 400, 300. What's happening there? Why is it stepping down? Why are we losing power at every stage? Yeah.
From the electric into the mechanical, it's just losing it to heat probably.
And then from the mechanical to the actual ankle, it's just the transmission with the gearing ratio would be it's
Geared down.
most likely.
Efficiency. Yeah, so like that's right though. So like on the electrical side, we're putting current and voltage into this motor. It's going to convert that electrical power to mechanical power, but in that process, it's going to burn off some of it as heat. It's going to raise the temperature. And we're going to see a decrease in the maximum power. So go from 450 watts to 400, and then similarly, because of the inefficiency in the transmission, we see the power decrease again. So this is an example of a framework. Like we kind of just, in this class, we described this framework. Most recently kind of showed an example of it. Next class, what we're gonna do is go through this framework for your system. So we're gonna start going through the different components of that, modeling the different parts, and eventually get to predicting its temperature rise. Any questions? Okay, we're gonna do a quick quiz, and then that's it.